Good evening, all professors and my friends. Today, I will present our research progress. First of all, let me introduce myself. My name is Christine Dewi from Taiwan University of Technology, Taiwan. So our research title, Traffic Sign Recognition with Visual Scene Understanding based on Deep Explainable AI. And this is the outline of my speech today. First is introduction, our cooperation, research outcomes and contributions, dataset, what's next, and summary. So in this project, focused on Taiwan traffic sign detection and recognition, we will combine machine learning with deep learning method for traffic sign recognition, and it can be used in traffic sign recognition and advanced driver assistance systems. We propose an efficient solution for real-time traffic sign detection and recognition using machine learning and deep learning. This research also focuses on designing deep convolutional neural network to improve the accuracy and provide meaningful explanation of the system with explainable AI. The cooperation and research outcomes and contributions. So far, we have 3 lists of published papers. First, deep learning for traffic sign recognition based on spatial pyramid pooling with scale analysis. And then the second paper, YOLO V4 for advanced traffic sign recognition with synthetic training data generated by various bands. And the last one is the robust detection method for improving small traffic sign recognition based on spatial pyramid pooling. So all of this paper already published. And if you're interested to read, you can download it online. Another paper is accepted, one accepted and one under review. So for deep convolutional neural network for enhancing traffic sign recognition developed on YOLO V4, we already get the letter of acceptance. Now still waiting for the publication step. And then the next paper for explainable artificial intelligence for image captioning using safely additive explanation. This one is under review. We already passed the second review and wait for the final decision. Now, first of all, we will discuss this related research paper about the robust detection method for improving small traffic sign recognition based on spatial pyramid pooling. And we can see in figure 1, this one is the color-based detection step. From the original image, we do the color-based detection step, including the mask red or blue, blur, binary, close, error, and delayed. This is used for detecting the red and blue sign, red and blue in our image. After that, we can get the features for each sign in the image. We will use this feature extraction in the next step. In here, the input image from feature extraction, so we already can get the small sign in the image. After that, this feature will be processed by our YOLO V3 SPP architecture to detect the bounding box and class prediction. After that, we will get the detection and recognition result. This is the example for this architecture. We can get the processing time and the size of the sign, and then the label class, the class label with the confident accuracy for each sign. We use the Belgian traffic sign dataset to evaluate the proposed method. We can see in figure 3, and this image contains of 1,628 times 1,236, with a total of 9,007 images in the dataset with 62 classes. The training performance on the PTSD dataset we can see on table 1. So while doing the training, we try some algorithm, YOLOV3, YOLOV3 SVP, DenseNet, and DenseNet SVP. We calculate all the loss value, the false positive, false negative, true positive, recall, precision, F1 score, IOU, and MAP value during the training phase. Okay, and based on this result on table 1, we can see that the YOLOV3 SVP reached the highest accuracy while training. Okay, this is the recognition result you can see in figure 4. So our system, our model can detect the processing time of each detection in the image with the size. We divide it by small, medium, and large. And then we also can labeling. Okay, we also can recognize the label based on each class with the confidence accuracy. In table 2, this one is the comparison of detection accuracy for our approach and previous research for small, medium, and large target. As we can see that our method, the combination of color detection plus YOLOV3 SVP with the PTSD dataset for small, medium, and large, we can improve the performance for each class based on the previous research results. For example, in the small target, we can get the accuracy 87.8, for medium 99%, and for large 99.6%. The next paper we want to discuss is about the explainable artificial intelligence for image captioning using sharply effective explanation. And the architecture we can see in figure 5. So the idea is start from the image data collection, the multimodal data that contain from the text or video. And for, in this case, we use the image data. We will do the captioning based on meta learning image understanding, and we will do the visual concept, text generation, caption re-ranking, and generate the final caption. And of course, we will explain the captioning with Sharp. We explain the models. So for example, this one, the output is a street with houses and mountains in the background. We will explain the Azure Cognitive service, use the open source image and then captioning model, and compare to analyze the result. After that, we will calculate the sentence similarity using SPACY and then factor TF-ITF. We'll also do the comparison and analyze the results. While the explainable artificial intelligence for image captioning using Sharp, the architecture of Sharp we can see in figure 4, as we see that data we will process using the models, and with the models we will do the prediction, and with Sharp we can explain its model and its prediction. In our experiments, we use 2 ways to describe image captioning, image to text as follows. First, Azure Cognitive Service and open source image captioning models. Our experiments will evaluate the image captioning result from each model using sentence similarity by SPACY and factor TF-ITF. We added a detailed analysis of the result of the sentence similarity evaluation. Now, in figure 6, this is the ImageNet data example. This is the image that we use in our experiments. For the result, we can see this image when we want to generate image caption from the Azure Cognitive Service. It will generate a snowy forest with trees, and the class is yes. For the open source image captioning model, the generates of image caption become a tree is standing next to a tree with a tree, and the class still yes. The image caption generation based on these 2 methods is slightly different, but have the same meaning. The next example, For the Azure Cognitive Service, will generate the image caption a red truck on the street, and the class belong to yes. For the next example, based on the open source image captioning models, the image caption, a truck is driving down a city street, and the class is yes. The next example, for the Azure Cognitive Service, a group of cars parked in a parking garage. That's correct. And then a bus is parked on the side of an airport. It's wrong. So we divide or we classify the class no. And then how sharp explanation for the test image. We can see in figure 7, the first picture in figure 7 is categorized as a coral reef, followed by a brain coral, honeycomb, and coral fungus. And then for the second picture, ox is the subject of the second image, right? And followed by the water buffalo, ox cart, and bison. The third image is classified as a jellyfish with the following probable class being handkerchief, tray, and face. Further, our matching image will be highlighted in the red superpixel. Now, based on the experiment result, we can conclude that we found Azure Cognitive Service give the most meaningful explanation for image compared to open source image captioning model. And our research work discovered that Azure Cognitive Service provide the best relevant explanations for image and achieve the maximum accuracy of 87%. SHOP can explain the top 4 most probable class for each image in our experiments. And based on our experimental results, we can conclude that the similarity with factor TF-IDF is better than spacing. Now, so far, we produced some data set. The first one is for Taiwan traffic sign data set. We can put it online through this link. And so far, we generate 4 class for Taiwan prohibitory sign using the no entry, no stopping, no parking, and speed limit. Another data set that's still ongoing is the Taiwan road marking data set. And we put in this link. For the Taiwan road marking data set, it concludes of 15 class. Our team focused on Taiwan road marking detection and recognition, and this is some of the result for the example. Now we're going to make the Taiwan road marking detection and recognition, the application and the data set. For adjusting eye aspect ratio for strong eye blink detection based on facial landmark, we can see in figure 1. We also still do the eye detection process using facial landmark. It's used for detect the eye blink, so can give the warning with the driver safety. We process the adjusting eye aspect ratio for strong eye blink detection based on facial landmark. We will make our own video data set. So we have the video with the challenge is the small eyes, glasses, driving car, afternoon and night, and labeling process using eye blink annotator. We will have our output. This is the data pre-processing. We will generate our own Taiwan eye blink data set. After that, we will calculate or detect based on the facial landmark using eye aspect ratio with different threshold, ER threshold. And we also will modify the ER threshold to analyze the result and for calculate the eye blink detection. Summary, we have 3 published papers, 1 paper accepted and 1 paper under review. And we built our own data set for Taiwan traffic sign data set, Taiwan road marking data set. We will explore more traffic sign identification and combine with explainable AI. Thank you.